Okay, in this video I'll be discussing exponential functions, differentiation, and integration. Basically, I'm just going to cover these three topics: the natural exponential function, which is also known as e, the derivatives of exponential functions, and the integrals of exponential functions. So the natural exponential function, also known as e to the x, is just a term used a lot for natural processes. It's similar to pi such that it continues on and on. It's the inverse of the natural log of x. So if you were to graph e to the x and the natural log of x, you can see that the two graphs are inverses of each other. They're symmetrical across that y equals x line. And just some basic rules about it that fall in with the natural log is, because the two are inverses, if you take the natural log of e to the x, you just get x. Similarly, if you raise e to the natural log of x, then you just get x. The natural log of e is just 1. And through these next examples, I'm just going to show how you can use this e to to evaluate equations and integrate and differentiate. So the first example is we want to solve for x when 4 equals e raised to the x minus 2. So what we're going to be doing is trying to find out what x equals, which means that we've got to isolate it somehow. Recall that if we can get the natural log of e raised to some power, then we can just bring it down to x. So here we've got the e raised to essentially x. So what we can do is we can take the natural log of both sides, and now these two would cancel out, and we have the natural log of 4 equals x minus 2. Add 2 to both sides, and this would be your answer for x. And you can use your calculator to get a decimal approximation as well. So for this one, we're going to solve for x when we have the natural log of 5x plus 2 equals 7. And in order to solve for this one, remember that when you have the natural log of something, that just means that you've got a base of e. So what we're going to do to get rid of this natural log so that we can isolate our x is we're going to use our log rules, and we're going to bring that e over and raise that e to the 7th power so that we get 5x plus 2 equals e to the 7th. Now from there we would subtract 2 from both sides and get 5x equals e to the 7th minus 2. Divide both sides by 5, and this would be your answer for x. Once again, you can get a decimal approximation by using your calculator. Now for the derivative of the natural exponential function, it's pretty simple to remember. There's basically just two rules when you're differentiating. First one is when you take the derivative of e to the x, you just get e to the x. When you take the derivative of e to the u, so that would be e to some value with where the derivative would be not 1, then it would just, your derivative would be e to the u times u prime, so times the derivative of u. I'm just going to show one example for this one because it's a pretty straightforward concept. Here we're going to take the derivative of e to the negative 2x squared. So in this case we're going to have an e to the u situation, so we're going to be using rule number 2. First thing we're going to do is we're going to have e to the u, so we're just going to bring down everything. We're just going to bring down this whole thing, and that's going to be multiplied by u prime. U in this case is defined as negative 2x squared. When you take the derivative of that and you get u prime, that equals negative 4x. So we're just going to multiply this by negative 4x, and this would be your derivative. Pretty straightforward. It can get a little bit more complex, but just remember to look for that u substitution and just make sure that you differentiate correctly. Integration, it's also pretty simple. There's once again just two rules. If you take the integral of e to the x dx, then you get e to the x plus c. That plus c is just there because we don't have defined limits. The second rule, e to the u du. If you take the integral of that, then you get e to the u plus c. So once again, I'm just going to show one example for this one. Should make it pretty clear. So here we have, find the integral of e to the 5x squared plus 6 dx. As you can see in this case, we're going to be using rule number 2 since our e is raised to a u in this case. So what we need to do is we need to just solve for e to the u. So if we think about our integration rules that we've learned before, the first thing that we'll do is we'll make a u substitution so that we get u equals 5x squared plus 6. And so what we're essentially trying to do is convert this dx into a du. So in this case I'll write du over dx equals, and the derivative of this is just 10x. We're going to multiply both sides by dx so that we get du equals 10x dx, and we just want to get the dx by itself. So du over 10x equals dx. Now we can make a substitution. I'm actually going to pull this, I'm going to think of this as 1 over 10x times du. So I'm going to pull that out in front. And there we have e to the u du. From rule number 2, if you take the integral of that, then you just get, we're going to bring down our 1 over 10x, and the integral of e to the u du is just e to the u plus c. so e to the u, and I'm just going to put the plus c outside of it. Doesn't really matter because c is just a constant. We're going to replace our u back with what we substituted for it. So we have e to the 5x squared plus 6, and then plus c. And then if you wanted to just simplify it and clean it up a little bit, and there would be the integral. So hopefully these concepts make sense. Pretty straightforward. Just remember that when you have that u, you're going to be looking to make a u substitution, and then you have to get, like the way I did it, I have to get on the right side something that's exactly in the problem. So I had to make sure to divide by 10x here so that I could get the dx by itself, because dx was the only part of that side of the equation that I had in my original equation. Yeah, and just remember that e is also, it's a value like pi, so it's not a variable.